Assalamualaikum and hi, my name is Fazrul Batrisha binti Abdullah, number matrix AA190566. So I am from Group Emerald. For today, Tasha and I will present on a case study entitled First Order Linear Differential Equations Applications. So for the introductions, exponential growth is a process that increases the quantity over time, or we can simply describe it as dn over dt. So from exponential growth equation, we can estimate the size of population and estimate the time of the population to achieve a certain amount by applying the growth equation. So the exponential growth equation is n equals to a multiplied with exponent power of kt. Besides, Sir Isaac Newton also has devised a formula called as Newton's law of cooling, where we can use it to calculate an object's temperature in relation to its surrounding. So the Newton's cooling law equation is T equals to the initial temperature of the body minus with the temperature of the surrounding multiplied with exponent power of negative kt plus with the temperature of the surrounding. So from this equation, it states that the rate of change of the body's temperature is proportional to the difference between the temperature of the body and the surrounding. So usually we can apply this Newton's law of cooling to calculate the temperature of a water with response to a time. So there are two case studies that we are working on. So the first case study is about exponential growth of bacteria in a liquid culture. And then the second case study is about Newton's cooling law application, where a girl named Elle wants to cool her coffee, which is the coffee is very hot at first, so she wants to cool it to a certain temperature by placing the coffee in different environment.
Assalamualaikum warahmatullahi wabarakatuh. My name is Natasha binti Muhammad Zain, AA190105, and for today I will explain to you about Fila table of case study P1. For the first fact is the number of bacteria in a liquid culture grow at a rate proportional to the number of the cell present. The second one is at the time t equal to 0, the initial time t equal to 0, there are 10,000 cells. The third fact is after 3 hours, the number of bacteria grow to 500,000 cells. And the fourth fact is an unlimited growth occurs after 1 day. And the last one is the bacteria double their amount of population. The idea of this case study is the rate of growth of bacteria is proportional to the quantity of the cells present, could be described as y prime equal to ky, which is k equal to constants. The capital letter A represent for the initial value in the differential equation of n equal to a exponent kt. The third idea of this case study is that the growth rate of constant of bacteria k is positive and k is more than 0 as it is a natural growth. When the bacteria growth rate increase, the population of the bacteria also increase proportionally. And the fifth idea of the doubling time of bacteria growth, we can conclude that n equal to 2 a initial. For learning issues, there are a few questions that we can come from this case study, which is first, what is the exponential growth equation? Second, how to find the value of a? Third, what is the growth rate of constant by referring to the number of population after 3 hours? Fourth, what is the number of bacteria, the amount of bacteria will be produced after 1 day? And fifth, how long did it took for the bacteria to double their amount? So for the action, in order to overcome the problems of the case study, the first step we need to know is n, which is the population of bacteria equation is n is equal to 10,000 exponent k multiplied by time. Second, the initial amount of the value a is equal to 10,000. By inserting n equal to 500,000, time equal to 3 hours, a equal to 10,000, we can find the number of bacteria growth after 3 hours. And the next step is 1 day is equal to 24 hours. So by inserting t equal to 24 into the equation, we will know that the number of bacteria growth is. And for question B, we are going to find the time of the bacteria doubling its size or its population. So we are going to use the modified equation, which is 2a initial equal to a initial exponent k multiplied by time.
So for Phila table for the second case study, so the first fact is the coffee case is warm at first and L1 to make it a bit cold. So the idea is we need to use the Newton's law of cooling. So how to write the equation and the actions here is we need to identify the given value and categorize them following the variables in the Newton's law of cooling. So the second fact is L took about 10 minutes to cool off the coffee from 76 degree Fahrenheit to 70 degree Fahrenheit. So the ideas that we can get from the second fact is we need to find the K value when T is equal to 10 and the temperature difference is 6 degree Fahrenheit. And then the learning issues here is what is the value of K with refer to the final temperature after being cooled after 10 minutes. So the actions for fact number 2 is we need to find the K value by inserting the value of T equals to 10 and NT equals to 70 into the cooling equation. So the third fact here is she used the ice to cool off the Victoria coffee. As she used the ice to cool the coffee, so the temperature of the surrounding will become 32 degree Fahrenheit, which is the temperature of the ice. So the learning issues for the third fact is how to determine the value of A. So the action is A is equal to the initial temperature of the body minus with the temperature of the surrounding. So the last fact here is the temperature of the surrounding is bright. So the idea is the cooler the environment, the shorter the time for the coffee to cool off. So the learning issues here is how to calculate the A value for every different temperature of the surrounding. So the action is we need to insert for every different environment temperature into the equation of A equals to the initial temperature of the body minus with the temperature of the surrounding.
For case study P1, we know that the problem stated is about the growth and decay problem. Commonly, the change of a quantity in a population includes the number of people in a country and the number of bacteria at a given time. So, if the population grow, the value increase over the time, and if the population decay, the value decrease over the time. And the rate of growth or decay is proportional to their size, and we can know from this from the equation below. P1, we know that the question stated that the number of a population growth of bacteria. So at the beginning of the experiment, which is T initial, is 0 hour, the number of bacteria is 10,000 cells. And after 3 hours, the bacteria have grown to 500,000 cells. So, for question A, to find the number of population of bacteria in 1 day, we needed to use the method of solving of n equal to A exponent kt, which is n is the number of bacteria present, k is the constant of proportionality, t equal to time, and A is the initial population. And for question B, we can find the doubling time of the number of bacteria by the modified equation, which is n equal to 2a initial exponent k multiplied by time. We are going to discuss about the case study N4. For case study N4, we know that the question has stated about the Newton's law of cooling as the temperature of the objects can be represented in a differential equation. So, when a high temperature object is placed in a low temperature surrounding, it will radiate heat to the environment and lowering its temperature. And the temperature. So, for the case study N4, Elle has bought a warm coffee but she wants to drink it cool. So she had bought several bags of ice. And the temperature of the warm coffee is 76 degrees Fahrenheit. And after 10 minutes, the temperature has dropped to 70 degrees Fahrenheit. To answer the question P1A, we know that the question stated that how to find the number of population after 1 day. So we know that the equation used is n equal to A initial exponent KT. We know that A initial, which is the initial population of the bacteria, is 10,000. Exponent with the K constant of T 1 day. So to find the K, we need to use the equation of 500,000 equal to 10,000 exponent 3K. To find K, after dividing 500,000 with 10,000, we will get 50. And after exponent both sides, we will know that K is 1.3. We will get the answer of K equal to 1.304. After 1 day, which is 24 hours, we will use the equation of n equal to 10,000 exponent 1.304 multiplied by 24, and we will get the answer. For question B, we know that the question stated that it wants to know the doubling time of the bacteria increase. So to find the answer of the question, we will use the modified equation of n equal to 2 initial population. So 2 we will multiply 2 with 10,000. So 20,000 equal to 10,000 exponent 1.304 T. So after exponent both sides, we will get T equal to 0.5316 hours.
So the solutions for questions N4, which is our second case study. So the first question A, we are asked to find the cooling equation. So firstly, we need to write the equation of dt over dt equals to negative K multiplied with temperature minus with the temperature of the surrounding. And then to solve it, we need to apply the separable methods. So we will put the dt, the small letter of t, at the right hand side, and then the dt with the capital T at the left hand side. So we need to integrate both of sides, and then we will get ln t minus ts equals to negative kt plus c. And then we bring the ln into the right hand side, and it will become exponent power of negative kt plus c. And then we need to let EC equals to A. The equation will become T minus TS is equals to A multiplied with exponent power of negative KT. So first we need to find the A value. So to find the A value, we need to insert T equals to 0. So after we have inserted the T equals to 0, we will get A is equals to the initial temperature of the body, T0, minus T as T surrounding. So then we will just substitute the A value into the cooling equation, and then we arrange it until we will get the equation T equals to T0 minus Ts multiplied with exponent power of negative KT plus temperature of the surrounding. And then after we have dropped the cooling equation, we just need to insert the A value and the temperature of the surrounding. So the A value here is 76 minus with the 32, we will get 44 degrees Fahrenheit. So that is the value of A, and then the temperature of the surrounding is 32. So the final cooling equation is TT equals to 44 exponent negative KT plus 32. So for questions B, we are asked to find the value of A. So to find the value of A is equals to T0 minus 50 surrounding. So we will get 76 minus 32 is equals to 44 degrees Fahrenheit. So for question C, the temperature of the surrounding has been changed. So the new temperature of the surrounding is 50 degrees Fahrenheit. So first step we need to do is we need to find the new value of A. So the new value of A is A equals to 76 minus with 50, the new temperature of surrounding, and then we will get 26 degrees Fahrenheit. After we have find the A value, we just need to find the K value. So to find the K value, we just need to use the T10 equals to 70, and then we insert it into the cooling equation, and it will become 26 multiplied with exponent of negative 10K plus 50 equals to 70. And then we just solve it as usual until we get exponent of negative 10K is equals to 0.7692. So to eliminate the exponent, we need to learn for the both sides. After we have learned for the both sides, we will get negative 10K is equals to ln 0.7692, and then we just solve it by dividing ln 0.7692 with negative 10, and then we will get K is equals to 0.02624. After we have find the A value and the K value, we just insert it into the cooling equation, and it will become 26 exponent of negative 0.02624T plus 50 equals to TT. And now we can find the times for the coffee to reach 59 degrees Fahrenheit. So to find the times, we just need to insert the TT equals to 59 and to the cooling equation. So it will become 26 multiplied with exponent of negative 0.02624 T plus 50 equals to 59. And then we just solve it as usual until we get exponent of negative 0.02624 T equals to 0.3462. So to eliminate the exponent, we need to learn for the both sides, and we will get T equals to 40.4245 minutes. So we can round it off to 40 minutes. So for question C, the new temperature of the surrounding is 40 degrees Fahrenheit. So we need to find the A value first. So A is equal to 76 minus with 40, and we will get 36 degrees Fahrenheit. So the new equation will be 36 exponent of negative KT plus 40 equals to TT. So then we will need to find the K value. So to find the K value, we just insert the T10 equals to 70, and we will get negative 10K equals to 0.8333. So we need to line for the both sides to eliminate the exponent, and we will get negative 10K is equals to ln 0.8333. And then the K value is 0.01824. So now we can find the times for the coffee to reach the 59 degrees Fahrenheit at the temperature of surrounding 40 degrees Fahrenheit. So we just insert the TT equals to 59 into the cooling equation, and it will become 36 exponent of negative 0.01824 T plus 40 equals to 59. And then we just solve it as usual until we get exponent of negative 0.01824 T is equals to 0.5278. And then we learn for the both sides until we get T is equals to 30 minutes. So result for the case study of P1 is shown in the table. We can see that as the time increases, the number of bacteria also increase. So as the K is over than 0, which is K is equals to 1.04, it shows that it is a natural growth, and we can conclude here that the exponential growth of the bacteria did satisfy the exponential growth model for the exponential growth equations, which is n equals to a exponent of kt. From the result for the second case study, which is case study N4, as shown in the table, we can see that as the temperature of the surrounding increase, the value of A, which is the difference between the temperature of the body and the temperature of the surrounding, did decrease. So a huge difference of the A value, it will give a shorter times for the coffee to cooling off. So what we can conclude here is, other than the influence of high ambient temperature, the value of A also could give effects to the time taken for cooling, as cooling is about radiating the heat and achieving the equilibrium with the surrounding.
So the last part, which is conclusion, the first order differential equation, which is exponential growth and Newton's law of cooling, can be applied in order to solve the separable equation for explaining the phenomenon of growing population in the case study P1 and the heat loss in the case study N4. And the K value can describe the rate of change of the current numbers of value with response to the time. And if K is more than 0, it will show positive or natural growth. And if K is less than 0, it will show a decaying process. And that is all from us, Emerald Group. Thank you.